There we go.
So,
Oh, this is just my non-disclosure or disclosure statement. So I'll mention this as I come along. First, before I start, I have to thank, I have a great team that Salvador Pani here is a co-director of the multi-scale robotics lab with me. We've had a lot of people through the lab over the years. And what's very nice is we're able to bring in a lot of different areas. I'm a roboticist. We've got medical engineers, electrical engineers, computer scientists, chemists, physicists. We've even got business people that work in the lab. So we've got a nice multidisciplinary group, similar to a lot of institutes, and I think that'll come through as you see what I'm going to talk about. A lot of what I'm going to be talking about fits in with the medical robotics area, and I think this is an advertisement I saw on the internet several years ago. And what I thought was interesting about it was they had this surgeon with photoshopped onto him a robot arm, and it says 1 part surgeon, 1 part machine, both parts amazing. And it's an advertisement from a hospital. And what they're saying is, come to our hospital and get operated on. Robots will operate on you. And I think what that says a lot. They're advertising, of course, the Da Vinci from Intuitive Surgical. But it's, this technology is being embraced by the public, by doctors, by hospitals. Over 10 million procedures have been done by the Da Vinci so far. And it's been a very profitable company, worth well over $100 billion. And it's making quite a bit of, there's a good profit every year. So that's encouraged a lot of folks to jump into this space. There's a lot of companies out there that are trying to, oh, you left your phone. A lot of companies out there that are trying to make a go of it. And I think it's interesting when you look at that. Da Vinci came on the market about 20 years ago. But there's been some recent movement that I think is quite interesting. One is this company Auris Health, which was recently bought by Johnson & Johnson a few years ago for about $3.5 billion. The other one is Intuitive Surgical, also has a, lost my pointer here. So let's see. Yeah, oh, there we go. Here we go. Intuitive Surgical also has a device that's trying to go deep into, both cases, into the lungs. So these are bronchoscopes. These are around 2 or 3 or maybe 3 or 4 millimeters in diameter. They're small but not super small. And the idea is to go deeper and deeper, in this case into the lungs, to get biopsies. And so the trends you see in the field of medical robotics, these are the products that are on the market, are towards smaller and smaller endoluminal devices that are going along more tortuous paths. And I think that's interesting because that ties in with a lot of our interests, which is, what's the next step? Well, the next step is there's a limit to how small you're going to make these catheters and endoscopes. They have pull wires in them. And they have to, there's only so much you can do. And so it seems like it would be logical that you're going to be actually releasing devices at some point. And that's what we're showing here is, this endoscope is going to get so small, and then you're going to be able to release these micro and nanorobots that are going to be able to go even deeper, for instance, deeper into the brain to do procedures that we really just simply can't right now. But we've got to think about the trends in this field and how it's going. But so in making these devices, there's a lot of fundamental issues in them. And one of those issues is materials and fabrication are absolutely key. That's the chemistry side of things. And this is what Salvador in my group, he directs in our group, I should say, he directs all the materials fabrication chemistry side of it on that. What materials do we use? What kind of cargo are they going to carry? Do they need, if they're going to go through the body, they should be biocompatible, even biodegradable in some sense. You want to be able to leave them in there. Can you see them? Can they adapt to how do they adapt to their environment, change shape, getting several of them to go together? So there's a lot of issues. And one of the key issues is how do they move? And we saw earlier about micromotors. We saw chemistry and light. I started here talking about magnetics. This is what we've been working on in the field. So I'm going to spend most of the time talking about magnetically driven devices by magnetic field gradients, or by rotating fields is what we use. But then as we heard of the chemistry, the light driven robots, there's some interesting work there. And I think there's some potential in that area as well. And then another person that came out of our lab, who's also a professor now at ETH, is Daniel Ahmed, and several others have been looking at acoustics and using ultrasound to drive these. So there's many different ways we can do that. But we focused right away, right in about 2003, on using magnetic fields. There were a lot of reasons that we like those. They're biocompatible. We have a good understanding of how they move through the body. And it seemed to solve a lot, or it helped us, I shouldn't say solve it, it helped us work on a lot of these problems. And so I want to just remind you a little bit about magnetic fields and field gradients and the way the mathematics, very simple math here, but there's two things you can do with magnetic fields. You can generate torques and forces on magnetic bodies. So if I have a field, I put a dipole in it. This could be a microrobot that's made out of a magnetic material like iron or nickel or neodymium iron boron or something. It wants to align with that field. It generates a torque. Forces are a little bit more complicated in that you move along the gradient. You move in the direction of where the field's getting stronger. So you've got this these two key pieces of information: how you generate a torque with a field and how you generate a force with the field gradient. You've also, of course, got the magnetization of the body and its volume as well in that equation, and these are all quite important. And so how do you generate these fields, as I was showing you here? You know, where are they coming from? And so that's a lot of what we've been focused on in my group over the years, is how you generate these fields and how you generate those field gradients. You know, we can generate one way we can generate a field is we get a bar magnet, something that's permanently magnetized, and it has a north and a south pole, and there are people that have been doing this for several years. This is a photo from Pietro Valdestri's lab at Leeds, and he's taken a robot arm, a KUKA arm, and he's put an electromagnet on it. A hard magnet, not an electromagnet, a permanent magnet on it. And as you move it around, then you can move the magnetized devices in the body. He's looking at right now. This is a paper on looking at guiding colonoscopes for doing a large intestine inspection. Here's some work that just came out last week in Science Robotics by a group, by Zhenwei Zhao's group at MIT. They also use a permanent magnet on the end of an arm, and they move it around to guide catheters in a patient, in the neurovascular part of a patient as well. But there's another way you can generate fields, and that's with an electromagnet, and that's what we're focused on. In this case, you take a current. Let me go back here. You take a current, you put it in, and you can generate a larger field. One of the advantages is we can reverse the field, and so then that changes the polarity, and we can also modulate it. So without moving the magnet, we can make the field stronger or weaker. Whereas with these kinds of systems, you actually have to move the magnet over the person. And I think there's some key advantages here with this approach. The obvious one is you don't have anything, nothing has to move. You can just put more, electrons are moving, but you just put more current in or out. The disadvantages, and one of the reasons that people do go this way, is you can actually generate higher fields with permanent magnets. There's some advantages there. But then the advantages here is that we actually have a much tighter control on dynamics. So we need to generate these moving fields. And so and the other thing I like is the math is a little more interesting to me too. So just being an engineer, I kind of like that part of it. So this is one of our electromagnets, one of our systems. There's a special patented way that we own the patent on, the way this is wound, and we can generate super high fields in it. We can take those and we put 3 of them together by coordinating the currents in each one of these, we can generate very special fields. And as a robotics person, it's very similar to the mathematics can be quite similar to how we move a robot arm. With a robot arm, we think of putting in joint velocities at each joint, and that ends up in guiding the end effector along a trajectory. And there's over 30 years of mathematics and controls from the robotics community that understands that very well. I think the last really interesting work, I should be careful when I say that, but a lot of this stuff was discovered by the 1980s or at least the late 80s, early 90s. In this device, it's just sitting there, but I'm actually controlling current in each one of those, and those coil currents translate into a specific field and a magnetic field gradient that comes out of it. And so I can very precisely control these really nice little fields in there, right? This is one of the I think contributions of my group over the years has been how we do this and how we model it. And if you think of a bunch of electromagnets, in this case, I have 8 of them together. Basically, the fields from each one of those superpose, they just add up. And what we were able to do, and one of the, I guess I would consider one of the breakthroughs in my group, was we were able to understand how we can take that physics of that and place it within the same kind of mathematical framework that we're used to as roboticists in controlling robot arms. And so then that allows us to bring all of these decades of work from not only how to control motion with this complicated mathematic multi-degree of freedom, multi-input, multi-output systems, but also how to design systems for optimizing that. And so that's kind of the robotics part of this. This is some patents we filed in 2010 that are still active and that actually generate a little bit of revenue, not a lot, but they generate some, they've been licensed. And like I said, yeah, published in 2010. And yeah, I'm not going to belabor this a lot, but it's quite similar. You know, we look at a, you know, in this case, it's a micro robot, and here's just simply 2 electromagnets. And by generating these complex fields and looking at where they are, we can understand, you know, if as we map in this space, we're looking at, this is in current space in those electromagnets, then we can look at the fields and field gradients we're generating and figure out where in the workspace can we generate useful motion, useful forces and torques to cause this motion to occur. And it's actually can be quite complicated. There can be voids in the workspace. You have to think about where can you control it, where can't you control it, when can you get enough control authority, and I'm not going to go into all the mathematics. But what's nice is there's this whole field of robotics where this stuff maps into that. And as you add more and more coils, for instance, this is one of our big 8 coil systems that we have in the lab that's large, it's used for large animal studies. We can fit a whole, human can fit inside of these. These workspaces can get quite complicated. And there's some really non-intuitive results that come out of this. This is a paper we published in 2015 with Andrew Petrisco when he's in my lab. And up until this point, nobody really understood the, you know, as you're adding more and more coils, why is it that we settled on 8 here? And we did all these numerical calculations, and 8 seemed like the optimal number, but we never really understood that until 2015, which we were able to prove that 8 is the minimum number of electromagnets you need to generate 5 degrees of freedom motion. And so when I say that, if this is my micro robot, I mean X, Y, and Z are 3 degrees of freedom, and then pointing about 2 of those axes. I can't generate this motion. So those 5 degrees of freedom I get out of a micro robot require 8 coils, and nobody had understood that before. In fact, there's some big research efforts that had gone down the wrong path and had used 6, which from a roboticist, you would think that's the intuitive way to go. So these kinds of results, I love minimum bounds or maximum bounds results because they know where you should shoot for, right, in your designs. And so over the years, we've designed a heck of a lot of robots. These electromagnetic navigation systems, we call them, or EMNSs, from the first Octomag systems to tabletop systems to, this is the CMAG I just showed you that does large animals, to clinical systems. And then we started, so we kept getting bigger and bigger, and then we started getting smaller and smaller. But one of the things, and this is where I'm going to talk about today, is the Navion. This is from this company, Nanoflex Robotics, that you heard about. It's they're right now putting this through a regulatory procedure. But what this has allowed us to do is very precisely control these devices with 5 degrees of freedom. And so this was, you know, until this 2010 work that I mentioned earlier, had really not, you know, nobody's really shown this level of control, of precision control over these devices. And so it all started looking at micro robots and how to move magnetic micro robots. This is particular one is made out of nickel. It's about between 1 and 2 millimeters long. But there's a lot of math in this plot here. This is from Michael Kummer's PhD thesis, by the way. But you'll notice the device is always aligned along the direction of the field, and what the colors represent here are when the field's getting stronger. In other words, the gradient. So it's always moving towards the red part, but it's always aligned that way, and that gives us a lot of control, a lot of understanding of the way these things can move. So we started thinking, well, what are we going to do with it? We started looking at in the eye. One of the advantages of working in the eye is that you can get close to it with the electromagnets, and also you can see them with an optical microscope. So we looked at taking some of these small devices and looking at how we might deliver drugs to the retina. This is a small animal. This is big enough for rabbits. We've done some animal studies, and this is one of our microrobots. It's about 1/3 of a millimeter in size. It fits inside of a 23 gauge needle and is able to puncture retinal veins. And so this is one of the areas we went down. But then we had a group around 2010 that started thinking, what else might we do? And they started looking at different applications. And one of the things they arrived at looking at was heart disease called heart arrhythmias, where your heart doesn't beat properly. And we realized we're not going to use microrobots to do that. But if we took the same mathematics we used before and we put a magnet on the tip of a catheter or an endoscope, we've got the same kind of mathematics that we can, so we can use all those patents that we developed before, and they all that applies then to guiding catheters, in this case in the heart, to do heart ablation procedures for treating arrhythmias. And so we went down this path, spun off company, developed a whole magnetic manipulation system controlled by a joystick. This is the system, a clinical system we built. You'll notice this comes apart in 2 parts, and then the patient can be prepped, comes together, and then this ablation catheter that's about 2.3 millimeters in diameter is put into the femoral artery and up the aorta into the right atrium. This is the control room where the surgeon is now sitting. You'll see this fluoroscope here. Normally, the surgeon's standing right here, pushing and pulling these and moving them. Right next to this X-ray, and if you're doing this 2 or 3 times a day all year long, that's not good. And there's somebody calculated if you happen to be an electrophysiologist doing this and you happen to get a brain tumor, 85% of the time the brain tumor is on the left side of the head, which is actually the side of the head standing there. So there is danger in this, and particularly if you go to some of the large hospitals like in China, where it's like a factory where they're doing this, it's quite dangerous for the surgeons. So we were able to take this all the way through did patients with it. We learned a lot. The nice thing about these electromagnets is you just run current. There's no moving parts, or maybe as a pump to do some coolant in them, and that's the key, is getting the heat out. But there's no moving parts, so the systems function very reliably. There's some training, especially for the older surgeons who aren't used to playing video games. They need a little more training. But we also realized as we went down this path, we were using catheters that were made by medical device companies. We didn't have enough funds to do the whole medical device approval, so we were using commercial off-the-shelf catheters. And we also realized right away the system's too large. If you ask a hospital to invest the millions it takes to modify their operating room, to put this system in there, it's a big ask for a new technology. And so we started rethinking this whole equation. The first thing we started rethinking is, what if we design our own catheters? What if we start looking at how these catheters move? And you realize, if you think about a catheter and endoscope, you want to push a rope. You want it to be flexible, but you need it to be stiff at times as well. And so one of the things that Christoph Schautum and my group did for his PhD thesis was looked at variable stiffness materials. In this case, we used a low melting point alloy that melted just above body temperature. And so then you can actually make different segments in the catheter, either stiff or flexible, whether you could heat it up just above body temperature and then use the magnetic fields to move it around. And at the time, we were able to develop what we called the world's smallest steerable catheter. It's about less than 1 millimeter in size, and it has 3 segments. And then by selectively softening segments, we were able to make it move. And then we've moved on now also to using thermoset polymers, shape memory polymers for some of this, and have gone down that path and filed some IP. The other thing I mentioned was taking control of the catheters. The other thing was rethinking how we design these electromagnetic navigation systems. So magnetically guided devices is not a new idea. There's a company out of St. Louis, Missouri called Stereotaxis that has been doing this for about 20 years. They also came to market right about the time Intuitive Surgical, and they were also looking at electrophysiology procedures. They're still on the market. They've got somewhere between 100 and 200 systems out there. What they've got are these two huge permanent magnets. This is their earlier system. This is one that just came out a couple of years ago, or a year or so ago. There's a 290 kilogram permanent magnets. They move around. So that means, first of all, it's slow. That also means you can't turn them off. Okay, so one of the advantages of electromagnets is you can turn them off. These things are always on, so you have to be aware of that. And so that also means the operating room has to be dedicated to those, because there's always going to be a magnetic field from those permanent magnets. Our first system was a bit of a hybrid system, because it could come apart. You could use the cath lab for regular procedures, but then you could bring it together and use it for magnetically guided systems. But our goal was to make portable systems, and that's what we call the Navion. Our first prototype came out in 2020. They do not generate as high fields as some of these others. We're doing better than this now, though. But we can get them closer. They're safe, and now that we've redesigned our catheters, that also means we don't need as high magnetic fields, and so that also gives us some advantage. But you see, we've gone from 7-ton systems to systems that are around 350 kilograms that can be pushed by a single person in and out of the operating room. And in fact, you can set this up. If you have, all you need is the right electrical connector in the wall and tap water coming in and out to remove the heat. And if you have all that infrastructure, which is pretty easy to put into an operating room, you can set one of these up in about 10 minutes, bringing in, set it up and get it going. And so that all of a sudden becomes a lot more attractive to hospitals too, right? Because they can test it out. They don't have to create it, invest a lot in it. I mean, they have to invest time. So it's not just an easy decision, but it's not like they have to find capital equipment budgets and all these kinds of things that can be a challenge when you look at systems like these here, where you literally, it's going to cost you millions, and you're going to take an operating room out of action, and it's going to have to be reconstructed in a lot of ways as well. So so this is where we are. This is Nanoflex, is a company that was just been founded very recently. The core part of it is the electromagnetic navigation system, also the catheters and the endoscopes. And so we have a number of patents on various parts of this. The other part of this is the advancer. So you put the catheter in an advancer, it moves it back and forth while the tip is being steered. And then of course there's the software, and this is all the robotic stuff that goes in here, and the operating systems and all that stuff thing that goes in there. These are some of the devices we made. This is on the left here is showing that we can move through free open space. This is very, very challenging to do with current catheter technology. This represents a big aneurysm, and you've got to get across that. And that's a real challenge for interventional neuroradiologists to do. We have patents on the variable stiffness device, and then we have a very highly maneuverable catheter that can actually tie itself up in a knot if you want it to. Not that we'd want it to, but I don't know of any catheters on the market that can do that. There are no catheters on the market that can do that. I think there's a paper that I saw recently that well, I should say, I just reviewed it. It should come out soon, that maybe they might be able to do that, but we've been doing this for a few years now. So these are extremely dexterous catheters that we can move hopefully deep into the brain, and they can also be very, very small. We've gone down to steerable catheters less than 300 microns in diameter. So if you want to do that, you can go down that path. This is in my lab in our lab at ETH. You see the Navion. This is a human vasculature. This is the aortic arch here, the aorta. This is that's what you're seeing right here. This is one of the first challenges an interventional neuroradiologist does, is try to guide this up one of the carotid arteries, the inner outer arteries, deep into the brain, and making these bends here can be a challenge. We use game controllers. We actually have developed our own, but the first one we used were PlayStation controllers, which actually look, it turns out Auris, a company I mentioned previously, has a device on the market. They kind of model theirs after Xbox controllers. This is our variable stiffness technology, where we bring the catheter up the aortic arch, get it in there, and then we can have a microcatheter come out of it. We lock it in shape, and then the microcatheter can come out of it, and then be further guided with magnetic fields deeper into the vasculature, deeper into the brain, into small vessels. And then this shows the Navion right here, guiding one of our highly dexterous catheters through relatively complex anatomies. These are extremely challenging to do with the traditional catheters. In fact, I'm don't think some of these you could do some of these kinds of motions with those. We've gone to animals with these. This is Philip Gruber, who's an interventional neuroradiologist. Here's with one of our catheters. This is a pig on here. There's the Navion and the fluoroscope. And this is about a year ago he was doing this. This is our little device going through. We're getting into vessels that are smaller than 1.5 millimeters in diameter, and able to guide it all the way up into the different branches, even able to make very, very sharp turns here, which when he did this said, I couldn't do this with my current tools. So he was able to make this turn right in here and go down this pathway. So those kinds of things, map very, very well, very nicely into what these interventional neuroradiologists currently do. They're still very similar. He likes to stand next to his patient. We wheel in the Navion, and then instead of doing this and twisting it, he's just guiding it with the PlayStation controller here. So that's some of the work we've been doing on the robotic side, but we also have been working for years on going smaller and how we can go in this direction. Can we make robots, the size of red blood cells and do something interesting with them? And so like a lot of folks, we get inspired by nature, bacteria. Howard Berg, who's one of the discoverer of the rotary motor of bacteria, of flagellated bacteria like E. coli and Salmonella, calls these nature's microrobots. They're around a micron or two long. They have chemoreceptors on them. Those are the sensors. They have a motor on them. There's a communication pathway through this motor that has an influence on its motion to tell it whether it's heading in the right direction or not. And there's also software in there in the DNA plasmids that are floating around, telling it what proteins to make. So there's actually, it is a robot in a lot of ways. As I mentioned, Howard was the one. Bacteria were first reported in 1675, but it was almost 300 years later when they discovered they had this rotary motor. And so we've gone down the path of looking at the fluid dynamics of this and understanding what the advantages of that are, and then bringing some of our nanotechnology to bear on this. These are nanoribbons that we made. This guy is one of our bigger ones. He's about 60 microns long, with a 20 nanometer thin ribbon in it. We put a little magnet on the tip of it. I can't make that rotary motor, but I can make the flagella. And so by rotating a low field, and these are millitesla kinds of fields, it propels forward, with very, very similar fluid dynamics than a bacteria used a flagellated bacteria would use. And so it's we've gone down this pathway a lot. We've looked at functionalizing them. We've looked at new ways of making them. Those first ones were made out of gallium arsenide, indium and indium gallium arsenide. Now we can make them out of polymers using the nanoscribe and 3D nanoprinting. This is what students do when it's late at night and they're looking for a nice project. This is in the Guinness Book of World Records a long time ago. We're making them around the size of a red blood cell. This is a human hair. This is about a red blood cell size, and these are some of the smallest ones we're making, on the order of a few 5-10 microns long. Costas Kostarelis, who you all know, we worked with him and published a nice paper in 2015 where we took 80,000 of these, we call them artificial bacterial flagella, 80,000 of these. We tagged them with a near-infrared dye, and we injected them into the peritoneal cavity of a living mouse. And we call those functionalized ABS, and these are a swarm. So this is literally a swarm of these. And so then, since the skin is thin there, and the skin is transparent to infrared light, we're able actually to see them. And so this shows that cloud of 80,000 being driven around. And like I said, this is with Costas and some nice work that came out of that back in 2015. So showing in vivo that we can drive these things and do something interesting with them. In this case, just look at them and move them, but you can imagine putting drugs or something on them. We also then thought about, okay, those are all relatively rigid, but of course in nature we know a lot of microorganisms aren't rigid, and they change their shape, their morphology. One of the microorganisms we became interested in was a parasite called Trypanosoma brucei, that is responsible for a nasty disease, African sleeping sickness or trypanosomiasis. And the life cycle, this thing lives in the gut of a tsetse fly. It bites a human and swims in the vessels and then moves across the blood-brain barrier and causes this deadly disease. But what was interesting to us is that there's a number of different morphologies this parasite takes throughout its life cycle. One of them is a long, slender form that allows it to be motile and move nicely. And the other is a stumpy form when it gets to where it wants to be and doesn't need to move and just kind of consolidates it there. So Henwei Wang in my group and Stefano Fusco, who did a lot of the initial work, developed polymers that were able to change shape by just raising the temperature a little bit. In this case, what we did was we put graphene flakes in a polymer. Those graphene flakes, of course, absorb infrared light very well, heat up, and then this hydrogel is able to swell and change shape. And so we're able to demonstrate deformable structures that we can trigger that through light. But what was also nice was that we developed this is the nice thing about having a chemist like Salvador in the group, where we can develop this process, this procedure, and actually test out the fluid dynamics of different designs and try to optimize locomotion capabilities. So now we have a way of making different shapes and then trying to understand how we can optimize those dimensions. And then the last thing I want to tell you about is how can you make a programmable microrobot? Okay, I'm a roboticist, we make these things and then all the programming is back here. How can we actually encode behaviors in them and change those behaviors? How can we make a programmable device? And so this is with Laura Heiderman, who's into nanomagnetism. She's at the Paul Scherrer Institute in Switzerland as well as ETH. What's interesting about nanomagnets that I didn't appreciate until Laura explained it to us is, well, we knew that super paramagnetic devices, single domain magnets, and then multi-domain magnets. But there is a region in the hundreds of nanometer size where the coercivity, that hardness of our material changes in a very interesting way. And that is we don't change the material, we just change the shape. And by changing that shape, we're able to generate various anisotropy curves. So now we can, by using the same material, but by patterning it differently, in this case, we're doing cobalt nickel, I believe, we can change this coercivity and get completely different behaviors out of these guys. And so we bring all this together with soft structures. And in this case, each one of these panels has different size particles. One of them will have a smaller and some of them will have larger shapes on them. And then by exposing this structure to different magnetic fields of different strengths in different directions, I can magnetize certain panels in certain directions. And that's a way we can encode them. We can program the behavior in that sense. And so with this panel of 4 different shapes, I can encode them in multiple different. I can make it a permanent magnet in one direction, or turn it off, or make it a permanent magnet in a different direction, and that allows me then to generate with the same fields, generate completely different behaviors. So here again is that 4-panel spring. Each one of those panels, then as it gets exposed to a field, certain panels going to remember its field. And then I give a weaker field. Well, this guy's coercivity is higher than this, so he will remember this, but then this one's going to get remagnetized in that direction. And similarly, in this direction, I can do it the other way. And so from 4 panels, I can actually generate 16 different behaviors from this one structure. So that allows me to take a single structure and in situ reprogram it in 16 different ways, and that it can behave. So it can behave differently. And then when you have interesting students like Chu and Wang on here, then they took this even further, and they started thinking origami cranes, of course. Why don't we actually put different patterns on this crane and pattern these? And again, this is with e-beam lithography, and it's not trivial to do these kinds of things. And now we can start encoding different kinds of behaviors in my cranes, or in our cranes. So the first one is to get it to flap. Okay, so this it's just moving. Okay, it's not really flying. I showed this recently, and somebody thought it was actually flying, so it's not. It's just flapping. Okay. Then by changing the way we encode it, and that's kind of shown here with these vectors, how we change that, we can get it so that it will want to turn. We can get it so it shows this kind of hovering motion. And then this is kind of a side slipping motion. So this same structure, we've got these 4 different behaviors. We could have a whole bunch more if we wanted that it can exhibit. So we're kind of moving in that direction. So of encoded structures. I think there's a lot more you can do here. And there's a lot of numeric, a lot of things roboticists really love about planning and motion and trying to think of complexity and all these things that can come into place here. So I want to kind of wrap things up. Electromagnetism remains our actuation method of choice for medical robotics. We've looked at other things. I'm always interested in seeing what other folks are doing. I think that's interesting, but we've gone down this path. Nanomagnetism, we became interesting. We understood how we can develop programmable devices, and I think there's more that can be done here. We continue to work on that. There's a lot to explore experimentally and theoretically that at many different levels. I think there's a lot of things you never thought of weren't really understood, and that's where a lot of the PhD students are going down on this. On the side of medical robotics, I just want to, there's been success. The field is clearly a success. There's a lot of investment that is going into it, that has gone into it, and there's been some commercial successes. But it takes a long time to get ideas out. What they say, every overnight success takes at least 10 years. I think in this area, it takes at least 20 years, probably. And there's a lot of reasons for these failures that we've learned over the years. And one is we're interested, as roboticists, we often underestimate the complexity of the problem. I think all science and technology people underestimate how complex these problems are. We probably wouldn't have gotten into them in the first place. But that's okay. The other thing we know as engineers is how important now it is to really work closely with surgeons and understanding their workflow and how do you integrate within them. You don't just go in and say, oh, I got this new device, you want to try it. You want to understand what they're doing, see what their needs are, and bring them little, incremental improvements to what they're doing. Then they're more likely to encourage that, to use that. And I think that if you want to kill a paper, in science robotics, for instance, just say, oh, this is an incremental result, right? And we still publish those sometimes, which I get upset about. But anyway, that's another story. Incremental is good in these cases. So you gotta figure out that. And then also understanding the business models. Why are we looking at certain diseases and not others? And how do those play out? But one of the questions in the long run is this really going to impact access to surgery worldwide? There's almost 8 billion people in the world right now. 5 billion of those people do not have access to safe, affordable surgery, right? And there's a lot of need out there for more and more surgeries. It's estimated that 1/3 of human disease is amenable to surgery. So we hear about things like HIV, tuberculosis, malaria. Those are the big. But that's only about 10% of the global disease burden. Whereas, access to surgery, you're going to be able to address a lot of people and make a big impact with that. And to do that, we obviously need to bring the cost of these systems down. It shouldn't just be what we call the global north these days, the developed world like Switzerland, Spain, United States that has access to these systems. But then also one of the things we find is that we think these technologies, as they get further developed, is that it will hopefully democratize surgery. It will make it easier for surgeons to be trained on more standard procedures. So we will be able to bring surgeons up to speed more quickly. Instead of spending 7 years learning how to be an interventional neuroradiologist, you could maybe do it in a much shorter period of time. And the other thing is being able to operate these things remotely. So a big population center like Barcelona, yeah, there's a lot of excellent first-class surgeons here, but if you go into less populated areas, there's not that area of expertise, and so that also we think is going to be one of the keys, and we see possibilities there, but these are probably longer term, but certainly worth looking at from a research standpoint. So I'm going to end it there, and I thank you very much for your attention. So.
Thank you very much. Thank you very much, Brad, for this really inspiring, fascinating talk. So we are going to open the floor for questions. I think that we will have both questions probably from the audience here, and also So I was saying that they will have probably questions from the audience here, but also in the chat. I cannot see the chat, so you can help me from there. Okay, so first questions. Let's think about question from here from the audience. Yes, we have here one first.
In the first part of the talk, you told us that you needed 8 electromagnets to have full degrees of freedom. But in your last system, you seem to have only 3. Yeah. What degrees of freedom are you losing?
So that's because we're only steering the tip. We aren't providing we're not controlling the gradients specifically. We're only controlling the direction of the field to steer it, and we're pushing it from the back.
Okay, so you're rotating mostly, not moving like that.
And so if you look at the Aeon system, that was built with 7 magnets instead of 8, the big one. But that's because we could pull out a degree of freedom because we're actually with the advancer. So it changes the mathematics of it a little bit. But is the least we need for that problem. But we could bring 2 together to get 6, and so then we can do some other things with it. So there's other possibilities there. So the real goal, while we're steering catheters with that, but my real goal is to steer microrobots with it eventually. But I don't necessarily need to control a microrobot with 5 degrees of freedom. I may only need to control it with 3 or 4 or whatever.
I have another question. The second part, you mentioned a few materials, but none of them is approved by the FDA. Are you thinking about using iron oxide, which is the only one approved?
So whenever when we do the catheters, we use neodymium iron ore, of course. But we know that's coming out. It's tethered, so it comes out. But whenever we do something in vivo or something untethered, then that's with iron oxide. And so Salvador is leading a big EU project called Angie on microrobots, and so everything they're doing is biocompatible. They're using iron oxide. They're using but anyways, using also the standard contrast agents and everything in there. But that's what makes the microrobot problem particularly challenging. Yeah. There are a lot of cute microrobots in papers out there that have neodymium iron boron particles in them, which is a non-starter, right? Like, well, it's good, and everybody says, oh, the fantastic voyage, you're going to cure disease. I'm like, no, you're not. You're not going to. It makes a great video, but it's never going to be a microrobot. It's going to be in a person, unless you can guarantee you get it out, and you can't with these really small devices. So it's a big challenge, and that's why we have a strong materials group in our labs.
Thanks.
Okay, any other question from here? Yep, yeah.
Hello, Brad. Thank you for your talk. It was very inspiring. I have a couple of questions. Well, at least one. I will think about the other later. It's about, is your product or your research only focused on operations, like surgical procedures focused only for, helping some people with a certain disease? Or do you also focus this on, for example, neuromodulation?
So we I had thrown a slide in here on our DBS work. Don't make a mistake. So we have worked on deep brain stimulation, on guiding electrodes through soft tissue, through brain tissue. Yeah, that's funny because I just remember putting that in there after our talk this morning. So we've done that on how to guide those. We thought with Salvador works on magnetoelectric materials, and so there's some really interesting possibilities there where instead of having wires guiding, you could actually use fields to generate the charge to treat the STMs deep in the brain. So we have interest in that, and we still have some very fundamental stuff, like the last encodable devices. That's very, very far out, but it's these are interesting. We just made a little millipede robot that walks, and it's very cool, and it's had
500,000 hits on YouTube, but it's generated some other ideas in the group for other things. So, but as when you get to be old like me in your career, you're starting to think, how can I take the technologies that we've been developing over the last 30 years, and how can I turn those into, get those out of the lab and into the clinic? And so then, I sort of refocus, in that sense. And that's a super big challenge. We love writing papers. We love getting papers published, but getting an idea out of the lab and into the clinic is it's a whole nother challenge, right? I think we all know that, right? And so so that's where, that's what I'm focused on in a lot of ways now, is how we could do that.
Any other question from here? I have so many, but I just have need to prioritize. So, I mean, it's a bit following up the previous one. So, I mean, in some of your work, you show that, I mean, you need to, or you decide to design also the catheter, right? Which adds complexity, I mean, to the work that you need to do, might not be compatible with standard procedures, etc. So, of course, then there is also the possibility to rasp, and then pull some existing device or existing lead or electrodes. So what can you say about what are the limits of that, right? In endovascular surgery, but also, we are interested in brain surgery, not endovascular. Is there a limit of the size of the material that you can pull, or the type of electrode that you can pull? What can you say about that?
Yeah, well, so, I showed those equations at the beginning, so I have a lot of answers to this. Torque and force, but you'll notice the big V in there for volume, and that's always it's always bad to see when you're a nanotechnology person, right? So there are limits as you get smaller, but that's when we move into the rotational motions, because those torques. So it's interesting if you look at the interplay between, for instance, if you're in a fluid, between rotational drag and the drag you can generate, they kind of cancel each other out. Rotational drag varies with the third power of dimensions. And so that's why bacteria were so brilliant to invent these rotary motors, because that is a very effective way of this rotational motion rather than pulling it with is a very effective way. So you rethink these things. And so this is one of the keys that we've learned over is rethinking the way we generate some of these motions. But the limits are always, you're going to be is just how much force can you generate. I mean, one of the advantages of the electromagnetic navigation procedure is it's safe, because you're not really going to damage, you're not going to do great damage and break through walls. So that helps your regulatory process. The risks are lower as you're in that part of the equation. But that, of course, means there's limits to what you can do. And so what those limits are, it takes, I think, it depends on how innovative you're going to be and how you're going to rethink some of these equations. And that's why we look at things. So we never forget about things like ultrasound or some of these other procedures that might be valid to use there. Okay.
I have more questions. So the other issue is like positioning, no? So you're using mostly fluoroscopy. I mean, do you think on other approaches more that can give you, they are less aggressive, let's say, or that you can also give you the same type of positioning when you position the robots?
So so whenever I talk to interventional neuroradiologists, people that do the intravascular surgery, they're happy with fluoroscopy. That's what they use. That's what they're used to. People have talked about using MR and doing interventional MR, but none of the people that are doing this day to day are going down that path. So fluoroscopy is good for that, but there is limits to how small you can see with fluoroscopy. We think a lot about contrast agents and what you can put on these devices to see them. There are also several groups that work on ultrasound and using ultrasound not just for guiding it, but also for imaging. And so there's a number of papers out there on that. And then there are mapping systems on the market. For instance, when you're doing heart procedures with these catheters, there's about three different systems on the market that don't use X-rays that can map where the position of the catheter is. They use electromagnetics. One of them uses an impedance approach, electrical impedance. So there are different ways to do that. And that's some of the ongoing work in our area is we take our catheters, we put a little Hall sensor on the tip of it. That Hall sensor can sense magnetic fields, and then if you've got these coils that are guiding it, but then you can also use those fields to sort of send a signal. And if you do the math right, you can triangulate where you are too. So there's a lot. I think there's a lot of possibilities here, but eventually the goal in all this in the end as a roboticist is to make devices that are smart enough to know where they want to go, right? So that'll be that.
The challenge is to make it then smart, but if you make it too small, I mean,
you know, see it.
or well, they cannot be that smart, right?
Yeah.
That's one of the issues. No, like if you make it too small, the complexity needs to be reduced, and therefore also the functionality. You know.
So people, I mean, there's folks like Sylvain Martel who does really creative, interesting work on using bacteria to drive things, because bacteria can go along gradients, and that's how they basically look at chemical gradients. And so, we can imagine devices that maybe will sense chemical gradients, maybe a temperature gradient or something like that. So
I'm going to read some questions. Let me check from the chat. Did you send it? No. Okay, so the first one is let me check. I was wondering whether the intensities of the externally created magnetic fields are innocuous for the human body, and whether there is a dissipation of these magnetic fields through the skin, or whether the operational intensity inside the body is way lower than the one applied.
yeah. So great question. And that's the reason that's exactly why we like magnetic fields, because first of all, the intensities we're using are, can be 10 to 100 to 1,000 times lower than an MR. So we know it's safe. They're not attenuated within the body. So it's just the big problem is they drop off with a cube of distance. And so they can drop off very, very quickly. But the real danger with magnetic fields is when they oscillate rapidly, and that's when you can get heating, and that can be the problem. But ours don't move nearly that fast. We're not at that range at all. So that makes that's again, you have to think about your regulatory process. If you really want to get this out of the clinic, and so that's one of the risks that are just disappear on us right away. So those are the important things to think about.
There's one question here. I think that. Is this one? Yeah. So fascinating presentation, truly appreciated. Do you think in the future would be possible to set a camera on the catheter?
We spend a lot of time on that. So every time I turn around, there's a company out of, I think it's in Taiwan where they're made, OmniVision, and they're making smaller and smaller chips. So now they're down to cameras that are around 650 microns in diameter, that are it's 200 by 200 or 400 by 400 pixels. So we think about that all the time. We spend a lot of time getting these people to ship us samples so that we can integrate them. One of the things that we've learned is we work pretty good with gastroenterologists, and they're used to their big endoscopes with high quality vision, so they can see things. They don't, just because you can go smaller, they don't want to take lower quality images. So doctors are happy to use something new if it's not worse, right? And so if the quality of the image gets worse, then that's a no-go. But we see these things getting smaller and smaller, and they're cheap. They're dirt cheap. So you can make these disposable. These cameras are, if they're that small and you're on a wafer, I mean, they're less than $1, and you could sell them for a heck of a lot more than that. So cameras would be great, and also. Blood is transparent in around, it seems to me around 1200 nanometers. I don't remember the exact number, but blood is fairly transparent in some of these regions. So you can actually we would be able to go into the heart and see tissue through blood. So there has been a paper or two I've seen on that. So that would be pretty interesting if you had near infrared imaging and you could actually go in and see that.
Is there any other question maybe for Maria Jose? I also have one for her. I have one for you, Maria Jose. So so you mentioned about the concentration. So you said that, well, it's working over certain concentration of salts, right? How is the velocity impacted by the range of concentration?
You mean in the Nafion?
In the Nafion, yeah.
In the Nafion. So it's a,
You can.
okay, it's very interesting. Yeah, okay. The question, Nafion has this particularity that the electric field that builds is proportional to the gradient of salt and inversely proportional to the screening. So you can compensate a little bit. We have been working with a 0.1 molar and it's working in concentration. It's because of this, because it's proportional to the gradient, to the concentration, yeah, and so the screening can be compensated a little bit, yeah.
There's a question from Salvador. One moment.
You can hear me, right?
No, but this is for the, sorry.
Oh, sorry. It's for her, not for you, Brad.
He knows all that. Yeah, he could ask me the hardest questions.
No. So when when you mentioned about the Nafion and all these things, are you thinking to use these swimmers for batteries?
In which ones?
The swimmers, like you would put this in the electrolyte and you would try to enhance the diffusion transfer of the electrolyte to the electrode. Have you thought about that? Like using these swimmers as an active matter electrode.
Yeah, for instance, to have a kind of a collective behavior and all these things, or more in the.
You're moving ions, right? In the battery.
Yeah.
You could use an electrolyte that is made of this active matter. You could enhance the diffusion of the active ions through the electrode.
Oh yeah, that for sure. That would be. I have never.
Repeat the questions for the people at home a little bit, please. Can you summarize it?
If I can use them, the swimmers, as for batteries, yeah. So that's the things. So it can be used. I was not thinking on that application, but it's quite inspiring for that. Yeah, it can be used. Yeah, for sure.
Okay, I think that we are going to leave it here. I would like to thank you both, Maria Jose, and of course also Brad, for this very nice presentation. Thank you very much, everyone, also for attending here and also online. Thank you.
Thank you.